At the advent of the French Revolution, a new universal measure was conceived, one that would be the same for everyone everywhere. Today we still use this measure, and we call it the meter. As opposed to local weights and measures, the meter was not derived from local economies or the human body, but from the shape of the earth itself. This, scholars argued, would lead to a measure based on a natural constant and would therefore be the same for all men everywhere. The meter was defined as 1/10,000,000th of a quadrant along the meridian. Since the shape of the Earth was then thought to be uniform and ellipsoidal, this definition would yield the same results for all longitudes. Not all meridians were equally easy to measure, however, and at the time the French proposed to measure a section of their own Paris meridian. But how do you properly measure a portion of the meridian stretching out over more than 1,000 kilometers? Rather than measuring the actual length, Méchain and Delambre, the astronomers tasked with this survey, measured the angles between different high points in the landscape. These measurements created a network of interconnected triangles superimposed upon the French and Spanish landscape. By determining the longitude and latitude of the beginning and end points, the locations of the measured portion of the meridian could be placed on the Earth ellipsoid. And by measuring a base, the total length of the meridian could be calculated. To carry out angular measurement, a special kind of telescope was used, the repeating circle, engineered by Étienne Lenoir and Jean-Charles de Borda in the 1780s. The repeating circle contains two telescopes that can be independently aimed at two different objects in the landscape. Most often, hilltops, church towers, or custom-built structures were used for measurements. The instrument was placed on top of one of these high points, and the telescopes were aimed at two other visible points. While doing this, the circle containing the scale was tilted to the geometric plane connecting the 3 points, thereby easing calculations. With this setup established, measurement could begin. The same area was measured several times in order to get more accurate results. To do this, the telescopes were alternated while the circle was rotated clockwise or counterclockwise. Astronomic measurements to determine the longitude and latitude of the beginning and end points were carried out with the same instruments by placing the circle in an upright position. The expedition of Méchain and Delambre resulted in the definition of the meter, which was officially adopted in France in 1799. The shape of the Earth as a natural constant, however, proved less reliable than anticipated. In fact, the surveyors' measurements were so precise that they exposed the structural inaccuracies of the ellipsoid model. The Earth cannot be captured in a uniform model, and each meridian would, in fact, generate slightly different results. Compared to contemporary satellite measurements of the Paris meridian, the meter is actually 0.2 millimeters too short. The great breakthrough of the meter expedition is not so much the invention of the meter itself, but that it started the search for a better model for the dissimilar shape of the Earth. This is today's gravity-based model known as the geoid. The meter, in the meantime, has been redefined on the basis of another natural constant, the speed of light. Its length is nevertheless inherited from the expedition of Méchain and Delambre, and serves as an enduring monument to their remarkable achievement.